So let's see the case of when we form a complex ion. Uh, we're going to see that many transition metals will be able to form complexes with Lewis bases, like water, hydroxide, cyanide, and ammonia, to name a few. These complexes are often incredibly soluble and have very favorable equilibrium constants that lead to their formation. In Discord, I'll go ahead and link a table of common Kf values, which are the constant of formation of these complex ions. And one that I'd like to study in this video is the the complex of silver ions and ammonia to form this complex ion that's circled in purple here. We can use this to increase the solubility of relatively insoluble silver chloride. Because what it will do by Le Chatelier's principle is remove the silver ions from solution, thereby allowing more silver chloride to dissolve. And we'll see, just like with any equation, I'm going to erase this purple bit now. We have a KSP for this first equation, the silver chloride dissolving, which is 1.8 times 10 to the negative 10. And then we have a Kf for formation of this silver ammonia complex, which is, I have it written here, 1.7 times 10 to the 7th power. So you see KSP very insoluble, right? We see that as an unfavorable reaction or unfavorable process. However, the Kf for adding ammonia to the solution is greatly favorable. So 10 to the 7th power. And so if we combine these equations, AgCl plus Ag plus ammonia, two ammonias, we get Ag plus Cl minus plus our complex. That the silvers, as we see, are the same on both sides, so we can get rid of those. So we end up with our silver chloride plus ammonia plus the chloride ion plus our complex, once we put these together. And as we know, the equilibrium constant, Kc here, would be equal to Ksp times Kf, right? If we add equations together, chemical equations, we multiply their equilibrium constants together. And so the equilibrium constant for this would be equal to 1.8 times 10 to the negative 10, and Kf would be 1.7 times 10 to the 7th, which would be, here we go, 1.8 times 10 to the negative 10 times 1.7 times 10 to the 7th. It's not U. Let's try that again. There we go. Which is 0.00306. So, slightly improved, right? A little bit better than before. Drastically so, in fact. With this information, let's go ahead and see the chloride concentration in just pure water and then with the ammonia added. So let's answer these questions. What is the concentration of chloride ions in pure water? And let's answer that same question in 1 molar ammonia. So we can go ahead and do this. The first one, we're just doing a KSP calculation because it's in pure water. So if we have our chloride, our silver chloride breaks into silver and chlorine. We have 0 of those to start. So we're going to add X to both sides. In our ice table, we get X squared equals KSP, which is equal to 1.8 times 10 to the negative 10th. All right, so therefore we just need to do the square root. So X is equal to 1.8 times 10 to the negative 10th. Square root that. We get 1.34 times 10 to the negative 5 molar. So that's the concentration of chloride in pure water. And we should see that with the addition of ammonia, we're going to drive this reaction to the product side, therefore producing more chloride ions, increasing the solubility of our salt. But let's do that. Let's calculate it to be sure. I have the equation written out here, so I'm just going to copy it. We'll do our ice table. Again, we don't need to worry about the solid. We have 1 molar here. We have presumably none of our original complexes, so we're going to subtract 2x here. We'll add x and add x. 1 minus 2x, x and x. We'll have, therefore, x squared over 1 minus 2x is equal to our Kc. This is the combined one. This is this number here, the one that we combined because we added those two equations together. We had to find a new equilibrium constant by multiplying the old ones. So 0.00306. And let's go ahead and bust out our solve for x widget. So we're going to have x squared divided by 1 minus 2x equals 2.00306. And let's get our answer. Here it is. A little too small to see. Let's get the approximate forms. Again, here we can't have a negative number, so we'll choose the positive one. So x is 0.052342. We'll get that out of here. That would be our concentration of chloride, right? According to this ice table, is just x. So, if we take a look at our original concentration of chloride ions, 10 to the negative 5th power. That's in water. By adding the ammonia, we have increased that to 10 to the negative 2 power. That's 1,000 times more. So we're able to dissolve our silver chloride such that we can now have a greater extent of dissolution happening by using a formation constant. Again, in Discord, I'm going to be putting up a table of formation constants as well as common complexes that are observed to form. And in our final video for this chapter, we'll take a look at pH effects, how adding acid or base to salts can help them to dissolve or not.